Hi everyone. We have already seen that independence does not imply conditional independence, which means that suppose two events A and B are independent, which means that mathematically probability of A intersection B is same as probability of A into probability of B. Then it doesn't mean that probability of A intersection B given C is also same thing, which means that given C also they are independent. Now it may happen that we have already seen with the examples, it may happen that given C they become dependent. So if two events A and B are independent, then it doesn't mean that given any other event, given C, let's suppose they are also independent, right? That we have already seen. But now in this video, we are going to see that conditional independence also doesn't imply independence, which means if two events A and B are conditionally independent, then it doesn't mean that A and B are usually independent, okay, without any condition. Let's just see with the example. Suppose I have this Venn diagram, and in this diagram, I will prove it that even though this conditional independence is satisfied, then also this normal independence is not satisfied, which means that even though this LHS is true, then also the RHS is false. That's what we will prove in this using this particular diagram. So let me go to the next page, and then here let me just write this Venn diagram, and then this formula is saying, let me maybe just note down this formula, and then I'm in the left hand side. So this left hand side is saying that conditional independence is true. Let's just check whether this left hand side itself is true or not. So if you just check whether the conditional independence is true or not, then what you need to do, you can just check that given C, what is the probability of A intersection B. Now let me do one thing, that let me just work intuitively, which means that given C, let me just tell you that what's going to happen. Now if this is the Venn diagram that you have, then given C you will be having something like this, where all the other possibilities other than given C will not exist. So this will not exist, this will not exist, and then everything else is allowed. Now here this is the diagram that we got after given C, right? This is the diagram that we have got after given C. Now here just tell me what is the probability of A intersection B. A intersection B here is just 1, right? Here is just 1 out of 1 2 3 4 5 6, right? Out of 6. So basically see what is happening earlier everything is having 1 upon this equally probable, and everything is having 1 2 3 4 5 6 7 8 9 10 11, right? So everything is 1 by 11. Now here, so earlier here everything was 1 by 11. Now here also everything is equally probable, but the only difference is that it will be 1 by 6. That's the only difference, right? Now here you have 1 by 6 because there is only one element common between A and B given C, right? And then that is equal to probability of A given C. So A given C, it is 2 elements out of 6, right? So 2 elements out of 6 into B given C. So B given C, which means 3 element out of 6. So let's just check whether it is true or not. This is 1 by 3. 3 cancel out. So yeah, this is 1 by 6 and 1 by 6. So which means that LHS is true. So this thing is true, which means it is actually conditionally independent. But now let's just check whether it is really independent or not. So conditionally we have checked that this is independent, but let's just check whether it is also true or not, right? So what is the probability of A intersection B? Here, right? Because given C, you don't want to know the probability, but probability of A intersection B will be, this is, I think only one element is common out of 11. So this is 1 by 11, right? And that should be equal to, see, this should be equal to probability of A into probability of B. Now this thing is coming out to be 1 by 11. Now probability of A is 1 2 3 4 elements out of 11. This is 4 by 11. Probability of B is 1 2 3 4 5 6 elements out of 11, 6 by 11. So since it is very obvious to see that 1 by 11 is not equal to 4 by 11 into 6 by 11, so that is why you will say that this is not true. This is actually not true, right? See, even though this left hand side is true, which means even though they are conditionally independent, still you are saying they are not normally independent, right? So this example is very good example which proves that conditional independence does not imply normal independence. So even though this condition is true here in this particular diagram, also like even though this is true, then also you can say that this particular condition is false, which means that conditional independence is true. So in this particular diagram, conditional independence is satisfied, still the normal independence is not satisfied, right? Okay, yeah, so this is the workout of the same example. Now this is summary where we are saying two events A and B are independent. If you can write like this, or maybe given B you can write directly with A, or given A you can write directly with B. If A and B are independent, then A and B complement, A complement B, A complement and B complement all are independent, right? Now, two events A and B are independent given C. So this is a summary. Now, given C, you say these are independent. If and only if you have something like this, which means if you say probability of A intersection B given C is same as, like, you can actually divide. You can just factorize it using the independence. You will say it is A given C into probability of B given C. Or you can say something like this, that this is equal to probability of A given B comma C, which means if A and B are independent given C, then given C doesn't matter that whether you have information about B or not. So you can write like this, or given C doesn't matter you have information about A or not. So you can write like this. So these three are equivalent definitions, right? And A and B, again, A and B are independent given C, then A and B complement, A complement B, A complement B complement, everything is independent given C. So in summary, you can say that this is normal independence. It doesn't mean they are conditionally independent. Similarly, they are conditionally independent doesn't mean they are normally independent, right? Okay. Now this is one optional read that you can have from a MIT book. This is the same thing that we talked about. Now let's just solve some questions. So this is the first question that we have. Now what they are saying is that given the following factorization, can we say that A and B are independent given C? Okay. So let's just check whether we can say that A and B are independent given C. So this is true false. So you just consider it we can say. Okay, instead of can we say, we can say. You can just read it out as we can say. Okay, let's just check if we can say or not. Now see, what they have given is that probability of A comma B comma C, that is equal to, they are saying you just factor it out using right hand side, probability of C into probability of, now you have A given C, that's okay. So let me write A here. Now probability of A given C, that is okay. Now into multiplied by probability of B given, it should be A comma C, but now you just have B given C. They are saying this is true, which means they are saying that these two are true, because in general this is a general formula, right? This is a general formula. But instead of that, what do you have? Instead of that, here you have probability of B given C, which means what? That given C doesn't matter whether you have A or not, right? So yes, you can say, yes, this is true, that you can say that A and B are independent. Actually, there is a symbol called independent. A and B are independent given C. Okay, this is some general symbol that people use for the independence. A and B are independent given C. Okay, if you just want to write A and B are independent, then just write like this: A and B are independent. If you want to write A and B are independent given C, then write like this. Okay, cool. Now let's move to this question. Now what this question is saying: suppose A and B are conditionally independent given C, then which of the following is or are true? Okay, let's just understand this. Now they are saying A and B are conditionally independent given C, right? Now, is this true? No. It means that if it is true, it means that conditional independence implies the independence. So obviously this is not true. So this is false. Is this true? Let's just check. See, now you have probability of C, which means maybe you are going from right hand side. Okay, just understand like this. This is probability of A comma B comma C, that is equal to probability of C into multiplied by, now you can consider this whole thing as a one event. Okay, just for the sake of writing, you can consider the whole thing as a one event. You can say A comma B given C, right? So now you have probability of C is matching, and A comma B given C can be written as B given C. Okay, I think this is in fact a general formula, right? Here you don't need any independence, so you can definitely write it as B given C into probability of A given B comma C, because you just forget about this comma C, and then it is probability of A or probability of B into probability of A given B, and now just write this given C everywhere. So you will be having this particular formulation. Actually, this is general formula which doesn't require independence. So whether it is true or not, tell me. Yes, this is true, because this is general formula. So this is true, irrespective whether you have independence assumption or not. Now let's just check whether this is true. Probability of C, now if you compare these two, the only difference is here, right? Now they are saying that you can rewrite this particular term as this particular term. Is this true? If A and B are independent given C, then you can omit this B. Yes, that is true. So that's why this is also true. Now let's just check it. Yes, A and B are independent given C, then you can definitely factor it like this. Then yes, that is also true. So B, C, D are true and H false. I hope you have understood this, right? Easy question, but a really nice question. Okay. Now let's just solve this particular question. What they're saying: mark all expressions that are equal to probability of A given B, given no independent assumption is given. I mean, you don't have any independence assumption. So let's just check it. So probability of A given B, right? Now let's just see the first example. What they are saying, that you can have the total probability with C, which means you can marginalize this C. See, just forget about given B everywhere. Can't you write probability of A equal to probability of A comma C plus probability of A comma C complement? Yes, right? You're just marginalizing this C, or maybe you are using the total probability formula, and then you can just write given B everywhere. So basically in the conditional probability also you can marginalize the things, right? So yes, that is true. So this particular option is true because this is the result of marginalization, or you can say this is the result of total probability. Now let's just see this, whether this is true. What they are saying, the probability of A given B should be equal to this. Okay, so let's just simplify this. This is ABC upon probability of B. This is probability of C upon probability of B. Now you will cancel it out. This is probability of ABC upon probability of C, and this is probability of AB upon probability of B. I don't think both are true, right? Because this is something else. Here you don't have C, and here you have C, but on just C. I mean, there is no C complement. I mean, you are not marginalizing or something. So this is probability of ABC comma divided by probability of C, right? See what I'm saying here is that you have in the option B. Okay, option B is coming out to be probability of ABC divided by probability of C, and what do you have in your hand is basically probability of AB divided by probability of B. Okay, so let's just do one thing. Maybe you can directly see that these two are not equal, but if you still insist me, then maybe I can do one thing. I can just rewrite this term as probability of AB into probability of C given AB, right, upon probability of C. I mean, just consider this AB as just one event and then do the factorization. Now what they are saying, that no independence assumption is given. So both are matching. Now here this should be equal to probability of B. I mean 1 upon probability of B. And I don't think there is any relation between this and 1 upon probability of B, right? So that's why, like, you can easily see that this option is not same as this option. Okay, cool. Now this was the option B. Now let's just do one thing. So this is A, B. Let's say this is C, this is D, this is E, this is F, this is G. Let's just check C. In C they are saying you are marginalizing, but you are marginalizing at given thing. So that's not true, right? I mean that is not not the marginalization stage, right? So that's why C is false, because you can marginalize, but you have to marginalize on the on this side. I mean not on the given side. So that's why C is false. This is false. Let's just check D. In D you are saying that you are marginalizing this AB, which means this denominator numerator is basically probability of AB, because C is just marginalization, and now you are marginalizing with probability of B. Yeah, so probability of AB upon probability of B. Yes, that is also true, right? What about E? So this thing is probability of B. Is this thing probability of AB? I don't think, right? So this is not probability of AB. This is clearly not probability of AB. See, probability of AB is probability of A into probability of B given A. But here you have probability of A given C. I mean this term and this term is not matching, even though this term and this term is matching, right? So that is why you will say this is not true. I hope you are understanding what I am saying. Why this is not true? Because the denominator is probability of B, denominator is matching, but the numerator is not matching. This is not probability of AB, definitely, right? So that's why this is false. What about this? This is saying, okay, I don't know what is this. Maybe let me just go to the next page and try to simplify this. Actually, I have a strong intuition that this is false, because there is no marginalization. You just have C. You are talking about just C. You are not talking about C and C complement. So I have a strong intuition that this is not true. But still, okay, sorry. This Venn diagram got copied. Let's just check it. So this particular thing is probability of A comma B comma C upon probability of B comma C into probability of A comma B comma C upon probability of A comma B divided by probability of C B comma C upon probability of B, right? This should be equal to probability of A given B, which means probability of A comma B upon probability of B. Actually, I don't think there is any sense in solving it, or I don't know if we can even solve it or not, because it doesn't seem that we have anything out of here, right? So this is completely different. I mean, this is completely different, and this particular thing is completely different. So neither I am able to cancel out few things, right? So if see, like these things are looking very different from this thing. This is AB. You have AB here, but that is in denominator. This is probability of B. Actually, like if you have the C, I was always sure that you don't have these two terms as equal terms, right? So that's why you will say that F is also the false option. Okay, so only A and C are the correct options. Let me see the answer. Yeah, A and this particular option, right? So yeah, sorry, A and D are the correct options. So yes, A and D are the correct options, right? Okay, now let's move to the next question. Now in this question, what they are saying, that mark all the expressions that are equal to probability of A comma B comma C given that A and B are independent. So just try it out and then we will solve it. I mean, just pause this video and try it out. They are saying that given that A and B are independent, what this expression is equal to. So let's just see this first option. They are saying probability of A, that is okay. Now generally that is equal to probability of A into probability of B given A. But since they are independent, that's why you can definitely write like this. And then yes, so I think this is true, right? So why that is the case? Because see, this generally, this particular term is probability of A into probability of B given A. I mean, you write from left or you write from right, does not matter. C given A comma B. Now this particular term has been written as probability of B. That is perfectly fine because A and B are independent. Okay, they are not conditionally independent, but they are independent to each other, right? So that's why this is perfectly fine. What about this option? This is saying probability of C into A comma C. Now this should be the last term should be probability of B given A comma C. Now B given A comma C and A and B are independent, then there is then given C they are not independent, right? See, given C they may or may not be independent. So that is why you will say that you cannot write it like this, probability of B given C. Because given C they may or may not be independent. So that's why this is false. Because this term and this term are matching. I mean, you can definitely, if you are not comfortable with the left, you can definitely write like this. If you just expand this will be probability of C into probability of A given C and then into probability of B given A comma C. Now this they are saying that you can replace this B given A comma C with probability of B given C, which is incorrect, right? The reason is very simple, because they may be dependent if C is given. So given C, they're independent, you don't know, right? Okay. Now let's just see this option. Probability of A into B given A into C given, yeah, this is general formula. There is no tension in this. This is general formula. And since A and B are independent, you can in fact rewrite this term as this term, probability of B only. But they have not rewritten, that's fine. I mean, this is general formula, that's fine. Now let's just check this option. Now probability of B and then C given B, that is okay. Now A given should be B comma C, right? B comma C. So this should be, in general, it should be A given B comma C. But now they have written A given C, which is incorrect, because given C, A and B are independent, you don't know. So that's why this is incorrect. So this option is correct, this option is correct. Now let's just see this option. Now what they are saying, probability of A given to A given C, yeah, that is correct. Now again, probability of B given C comma A, it should be C comma A, right? But now they are just writing C, they are omitting this A. So that is why this is false, because in the conditional independence is not given. Now let's just check this. Okay, just consider this A comma C as just one event. So probability of A comma C into probability of B given A, yeah, that is correct, right? See, what I'm saying here is that you just consider this probability of A comma C as one event. So maybe you can rewrite it like this, and then just consider this thing as a one box, and then it is probability of A comma C into probability of B given A comma C, right? See, A comma C into probability of B given A comma C. So I think this option and this option is correct. Let's just check the answer. Yes, these three options are correct. Okay, now let's solve more questions. So here in this particular question, I'm saying this time they're conditionally independent, right? This time they're conditionally independent. Just try solving this question and just let me know that which of the options are correct. So this time they're conditionally independent. Earlier they were not conditionally independent. So if they're conditionally independent, then I think you can definitely you can definitely write like this, right? Because that's the first thing that comes into mind when we say that these are conditionally independent. Okay. Now here you can write like this: probability of A comma B comma C upon probability of C. So this is basically probability of yeah. So this is probability of B into, yeah, I think that is a general formula. I don't think that there is any independence or dependence is needed here, right? Because they have rewritten this ABC as probability of B into, they've considered this AC as one event, right? So now they are saying B into given B AC. Yeah, that is a general formula. And now let's just check this and this. Okay, so let's just check this probability of C. They are saying the probability of C into probability of B given C. Okay, let me just do one thing. Okay, this is the thing, right? Maybe let me just do one thing. Maybe let me just open this up. Everything. Probability of C upon probability of C comma A comma B upon probability of AB. So I think this thing is getting cancelled out. Okay, this is AB. I don't think there is any relation between these two, because this is ABC, the ABC is coming, and then this is some pairwise probability. I don't think there is any relation, so this is not true. Okay, A and B are independent given C. So A and B are independent given C, right? So here I don't think I can even apply that particular formula. Okay, so that's why this is not true. What about this? This particular thing is saying that let me write like this. See, it should be A given C into B given C. They're saying A given B into B given C. So I don't think this is true, right? So that's why this is false. So these two are true. Let me check the answer. Yeah, these two are true. So these are the questions that we wanted to solve. I hope you have understood now that what is conditional independence, what is normal independence. And then we have solved some variety of questions which may or may not be asked in GATE. Like I'm not sure, but you should be very much clear that what is conditional independence, what is normal independence. And based on that, we have also solved some questions. So that's all I wanted to discuss in this video. Yeah, thank you so much.